So far, we have used the rectangular, normal and tangential polar coordinates to describe the motion of particles. The motion is measured with respect to a fixed reference axis, or what we call the Newtonian reference of frame or inertial frame. In this case, the obtained kinematic parameters such as the displacement, velocity, and acceleration are known as absolute motion. However, in many systems, it may not possible or difficult to use the fixed reference frame in order to observe the motion. In this case, we can perform the relative motion analysis by measure the motion with respect to a moving reference frame. The moving reference frame might be translate or rotate. In Newtonian mechanics, you have Newton's law 1, which is relevant to inertia. It states that a particle will remain at rest or continue to move in a straight line with a constant velocity if there is no unbalanced force acting on it. For the second law, the acceleration of a particle is proportional to the resultant force acting on it and is in the same direction with this force. Law 3 mentions that the force of action and reaction between interacting bodies are equal in magnitude and opposite in direction. This law will be valid only if the subject follows the assumption below. The measurement must be made in absolute frame of reference, where the axes attached to the surface of the Earth are sufficiently fixed and non-rotating for most engineering problems. So this is about the inertial frame. The measurement of the motion must be made in this inertial frame in order to make this law valid. For example, if the acceleration is measured from inertial frame, then we call the acceleration to be absolute acceleration. So in this case, when you determine the force by using F equal to ma formula, then you can find a valid force. If you find the acceleration from non-inertial frame, so in this case, the frame can be rotate or translate. So you obtain the acceleration in terms of relative acceleration. Then the force that you obtain from the relative acceleration will be not valid. So it's very important that you follow the assumption where the measurement must be made in the inertial frame to obtain valid result in the Newtonian mechanics. Not only the frame that is fixed or not moving or not rotating is considered the inertial frame. A reference frame that is translating with constant velocity or no acceleration is also known as inertial frame. In this case, you have two particles, particle A and particle B. Both of them are moving. And then you have an observer at point O. This observer is not moving, so we can call it as fixed reference frame or inertial frame. Acceleration B, or acceleration B that is measured with respect to O, is called the absolute acceleration because the O here is not moving. And then you have the acceleration A, or what we call the acceleration A that is measured with respect to O. Since O is not moving, therefore the acceleration A is absolute value. Then you have the acceleration B that is measured with respect to A here. So since A is moving as well, therefore we call this as relative motion. So you should know acceleration B is also equal to acceleration B slash O here. Slash O here means that the acceleration of B is measured with respect to O, which is the inertial frame. Slash A here means that the acceleration of B is measured with respect to the observer at A. Since A is moving, therefore we call this acceleration as relative acceleration. In many engineering applications, you may not able to measure the point here. Let's say point B cannot be measured directly from the observer at inertial frame. So in this case, you cannot obtain AB. If we can't measure the acceleration B from the inertial frame directly, we can still find its value by performing the relative motion analysis. If the acceleration at point A is known, and you can measure the acceleration B with respect to A, with that take the summation of these two values and you still can obtain the acceleration at point B. So this is called the relative motion analysis.